Hello students, I am Dr. Parin Sheikh from LG Institutes of Applied Sciences. This is my second video lecture on Mossbauer Spectroscopy. In first video lecture, we have discussed about the Mossbauer effect and its importance. Now, in this video lecture, we will discuss about the isomer shift and its different factors. So let's start. Chemical isomer shift CIS is also denoted as delta. The deviation of the spectral line from the centroid, it is known as CIS. It was identified by Krishna and Sunya in 1960 and they derived an equation for the CIS. The change in electrostatic energy on decay is also given by chemical shift or isomer shift. This is the equation in which where epsilon 0 is permittivity of free space, Z atomic number of the nucleus, E electronic charge, psi s absorber, s orbital wave function or absorber, psi s source, s orbital wave function of the source, and r is radius of the nucleus. Since s electron wave functions have their maxima at the nucleus, s electron density affects the isomer shift to a great extent. But changes in p and d orbital affect the s electron through screening, hence have a smaller effect on isomer shift. Here s electron has greater extent effect and p and d orbital has less effect or small effect on isomer shift. Where delta R by R is positive, the isomer shift is also positive, and if it is negative, which reflect the negative isomer shift. In short, we can say CIS is directly proportional to delta R and del psi square. Some factors first, that is Mossbauer spectra of Fe compounds. In case of iron compound, when combustion, so the value of delta R is equal to negative. In here, increases in s electron density, it will affect the CIS is also decrease. Increase in d electron density, the CIS increases. This thing we have to remember. For better understanding, CIS is equal to delta R and del psi square. So here the value of delta R and del psi square is negative. So CIS turns to positive. It can be understood by taking example of FeCl2 and FeCl3. The CIS of FeCl2 D6 is higher compared to D5 system in FeCl3. CIS of FeCl3 is 1.55 mm per second and for FeCl3 it is 0.66 mm per second. Why it is so? So we can understand by its electronic structure. Electronic structure of Fe plus 2. Fe having 26 atomic number. So here the electronic configuration is neon 3s2, 3p6, 3d6 and 4s0. In case of Fe plus 3, one electron is less in 3d5. There are more 3d electrons in Fe plus 2, means d6. So more shielding effect in Fe plus 2. So attractive force of nucleus on 3s electrons is less in Fe plus 2. Therefore, electron density in Fe plus 2 is decreased, means value of del psi square is negative. And as we know that del psi square and also del R value is negative. Therefore, from the equation of CIS, it is positive for Fe plus 2. So, CIS increases as 3d electron increases. For better understanding, here the plot of percentage transmission versus Doppler velocity. Here the value of Fe plus 2 is positive. Next, Mossbauer spectra of teen compounds. In case of teen compounds, there is expansion. So the value of del R is positive. Here increases in S electron density, CIS increases. Increases and D electron density, CIS decreases. Exactly reverse that of Fe compounds. So CIS is positive as delta R is positive and positive as del psi square is also positive. So all over CIS is positive. It can understand by taking example of SnCl2, CH3SnCl and SnCl4, where in case of SnCl2, 5s2, CH3SnCl there is 5s1 and SnCl4 there is 5s0. So the value of CIS is decreases. It can understand by solving the electronic structure of Sn plus 2. Here the more electron in 5s2 orbital, and in case of Sn plus 4, 5s0. Here delta R by R was positive for teen compound, that we know, and greater electron density in 5s electron. So del psi square becomes greater and CIS will be more positive. So CIS is positive for SnCl2. This is diagram of percentage transmission versus Doppler velocity. Here the value of SnCl2 is positive and the value of SnCl2 is negative. Third factor, that is CIS and electronegativity. The chemical isomer shift of halides of Fe plus 2 of high spin complexes have linear dependence of electronegativity. Here the complex of Fe and they are in high spin. Higher electronegativity on ligand, that means less electron density on metal, because the ligand tries to pull electron towards it, makes the metal electron deficient, which means more isomer shift, CIS will be increased. The electronegativity of halide, the order of electronegativity. Okay, I think here it is reversed. The electronegativity of fluorine is high, then chlorine, then Br, then iodine. So FeF2 having highest CIS as it is more electronegative in case of Fe compound compared to FeI2. FeF2 having 1.58 CIS, FeCl2 1.32, FeBr2 1.28 and FeI2 1.20. It is continuously decreases in case of Fe compound. Now fourth criteria, that is D pi P pi back bonding and CIS. To understand this, pi acceptor ligands such as carbonyl, cyanide, NO, they back donate the electron density, and due to this greater S electron density on metal atom, due to back donation of electron, the metal having more electrons and the S electron density increases. In case of Fe compound, as electron density is increases, which reduce the CIS. It can be understood by taking these examples, in which first compound having pi acceptor ligand cyanide. Okay. First we will see the pi accepting pi acidity order of the ligands. First NO, then CO, cyanide, ammonia and water. Okay. Here we have in first complex we have water. Water having lowest pi acceptor tendency. So its CIS is highest compared to the last complex in which there is cyanide and NO. They have higher pi acceptor ligands capacity. So they having 0 CIS value. Here as the pi acceptor ligand tendency decreases, the CIS value increases, which can be shown by this data. This is about isomer shift and its factors. Thank you.